Now we're going to talk about some additional programming options and features. First one we're going to talk about is max speed. Now 2000 millimeters per second is the fastest this robot is allowed to go. If you type in 3000, it won't be able to take it because the max speed for this is 2000. However, there are times where the robot can actually go faster than 2000 millimeters per second in a straight line. In order to be able to go that speed and not be limited to 2000 millimeters per second, you can go here, say choice, and say max speed. It'll now move in a straight line at its max speed. The reason this happens is because you can go faster than 2000 millimeters per second in joint mode, but linear has to have a maximum to give you. Still, there is that possibility that just due to the actual spot it's moving in, it's able to go a little faster. So if you ever need to speed up the robot, you can experiment with this max speed option. Another useful tool are timers. Timers can be added into the program to help you calculate cycle time, or if you need to actually wait a certain amount of time before the robot does something else. To set up timers, you go to miscellaneous, timer, and for the timers you actually have a few options. We'll go to setup, actually next page, data, no, status, program timers, there we go. You have 10 timers by default. There are ways to increase the amount of available timers, but we're not going to cover that right now. So let's just use timer 1 for this. I'm going to say timer 1. First, we want to stop it. We don't know what state it is in right now, so we want to stop it, and we want timer 1 to reset. And then, after all that, we would like the timer 1 to start. So right here we stop the timer, reset the timer, and start the timer. We want to know how fast it is to get to this position here and to the end of the program. So at the end of this program, we're going to stop the timer, and we're going to have register 2 equal the timer value of 1. So this way, from this position, from our motion to this position to when we get to the end here, we're going to be timing the robot. And then we're going to put all that into register 2. So if we run this program, let me pull up the registers right here. Shift forward. Alright, so for that it took us 3.2 seconds. You can run it again. Now because it actually started a little further back, it's going to take a little longer. There, 4.856. Now there'll be times where you need to keep track of multiple cycles. There's no real official way to do that except to make a history for this. What you can do is we're going to actually use timer 10 through 20. Now there are better ways to code this, just a heads up, but I'm going to show you the simple way so you get the understanding of it. We're going to say register 19 is equal to register 18, and register 18 is equal to register 17. We keep doing this. Okay, so we have our history right there, and that will give us a nice little plot right here as to the time it took for the last 10 cycles. So we'll be able to see it all there, and if we wanted to, at the end of this, we could do something like R9 is equal to R10 and then plus R11 and go all the way down to R19, and then say R9 is equal to R9 divided by 10, and we'd be able to get an average. I will not write that out right now though, so I'm going to just delete this. But this is a common way if you need to keep track of a few different cycles. Maybe you're having issues with consistency and you want to check to make sure that it's running at the same time, or you're not sure if this certain area is the area that's messing it up. So what we're going to do is we're going to put label 1 and jump label 1 and run the program. So now you'll see our most current time will come here, and then that'll move down, and then it'll keep moving down with each run. So we'll soon be able to get a nice history of this, and if we wanted, we could get an average of it as well. So this is a lot more useful when you're actually like picking up, dropping parts off, and the possibility of a variance in the cycle time is a lot higher. Still, if you ever need to prove that the robot's meeting certain cycle time, or if the robot is being delayed due to a digital input, you could always use timers to do this. This isn't really going to slow down your program at all. The robot runs extremely fast. I can't give you the full details on that, but it's not going to interfere with your cycle time by having something like this in there. Another aspect of this that you can take advantage of is the motion options. If you put your cursor right here at the end of a motion, you can press choice and you'll have a whole bunch of different options. One of the most popular options to use is acceleration right here. ACC is for acceleration. By adjusting this value here, you can adjust the acceleration and deceleration of the robot during this motion. So as it's moving to this point, it'll use this acceleration value, and as it's approaching this point to decelerate to it, it'll use that acceleration value as well. So if you had a very fragile area where you needed to go a little slower, then you could put an acceleration of 50. You can actually go above 100. You can go to 150 if I recall is the default value. That default value is set in the system configurations, which we'll be going over when we talk about creating a new robot. One thing I should mention about using a higher acceleration is that you will definitely decrease the lifespan of the robot motors because you are overclocking them, and it does increase the chance of an overcurrent alarm. Overcurrent alarms will require rebooting the robot, so that will definitely interfere with cycle time because you're going to have to stop the robot, stop production, restart the robot, get it back to home position, and start it all over. So this is something to take into consideration. Just be aware of it. If you're having overcurrent issues, then you should lower your acceleration back to a normal value. Another option is the timeout function. Now, when you have a wait, let's say you want to move to this position, but then you needed permission to move to the next spot. You could say wait until di1 is equal to on. Actually, we will say when do7 is on before moving to this next location. Now, you may want some conditional wait right here. You don't want it to wait there forever. If you don't get that signal, you want the robot to move away. So what you could do instead is you could say timeout, jump to label 1. Now for this timeout, you need to set what is your timeout amount before you can actually use it. There is a default value, but it's always best to set the timeout value beforehand so that you know what it is and anyone following your code knows what your timeout value is. So to do this, you have to put a wait amount right here, and we're going to say 100. Now what I just did there was I added a parameter in there. Parameters are basically system settings that you can adjust, but you need to be wary when you're doing that. So when I did this right here, that $sign means it is a parameter. So right there is a parameter. You can actually type them out here if you want. There are some specific parameters you may need to adjust which aren't given in this option page. These are just kind of the most common ones here. So wait amount is a common one, however, so I'm just going to use that one there. And for its value, I'm going to set to 100. Wait amount is in hundredths of a second. So if I set the wait amount to 100, that means that this robot will wait 1 second before timing out and jumping to label 1. So let's put that label 1 in there real quick. And we're going to actually move back to position 1. So we'll move from position 1 to position 2, and we'll wait for do7 to turn on. If it has not turned on within 1 second, we will jump to label 1, which is right here, and then that'll move us back to position 1. Now 1 second's a little short, so I'm going to set it to 5 seconds. And we are also going to adjust this to fine for the moment. So we will so when we run this, we move right there, and after this time limit has expired, it'll jump to label 1 and move back to that point. So when we run this right here, the robot's actually going to run in simulation. Shoot, I lost the controller. If we turn on this digital output, it will continue its code. However, if we run this again, and we don't have this on, it'll get to its weight right there, it will time out, and it'll move back to its position. So you can use this timeout feature if you have to wait too long and you might have to scrap the part because it has to remain hot or something like that, or if it should seek an alternative pick location. There are all sorts of options you can use for this. Another option is to use the skip function. So as we're moving towards a position, we can have a skip label. Before we can use the skip function, we must set up the skip condition. So we're going to insert a line. Before we can use the skip condition, we have to set the skip condition. So I'm going to insert a line, instruction, skip. Skip is equal to when DO7 turns on. So if we're moving to this position and DO7 comes on, then we will just continue on with the code. However, if we make it all the way to position 2, then we will jump to label 1. So the way I have this set up is it'll move to position 1, set its skip condition to digital output 7, turning on, and then it'll move towards position 2. As it's going towards position 2, it's watching for DO7. If DO7 comes on, then it'll immediately move to position 3, which is right below that line. If it makes it all the way to position 2, it'll jump to label 1 and thus move to position 1. So when I run this simulation here, the robot will move there, but DO7 did not come on, so it jumped to label 1. Now, if we turn on DO7, instead, it'll immediately break its motion and move to position 3. Alright? So notice it was going towards position 2, DO7 came on, it moved towards position 3, and then went back. Mostly, I see the skip condition used to stop a motion when the robot senses a part. So if the robot's going to a pick position, senses the part, it usually stops motion, saves the position, and then moves backwards. Another useful function is the time before and time after. Now this one's a little tricky because we can have a lot of issues with this one if it is not done correctly. So we add this motion option, which is time before and time after. We'll deal with time before first, and we'll say 0.5 seconds. Turn on digital output 7. We'll just pulse it on for 1 second. Now, going to open up the second window so we can see the I/O. We'll turn off DL7 right there. So the way time before will work is the robot will calculate when it will reach position 2, and 0.5 seconds before it reaches that point, it'll pulse on digital output 7. This time before and time after are part of the advanced constant path option pack, so you may not even have them available. Just keep that in mind. So when we run this here, as you can see, it turned on 0.5 seconds before it actually got to that point. 0.5 seconds was a little short, so we're actually going to do 1 second. So it should finish its pulse right when it gets there. So we'll run it again. It's a little fast there. We're going to drop that speed down. Alright, and there we go. Now the alternative is if we use time after, and we say 1 second. 0.5 seconds. Digital output 7 is on. So now, half a second after it passes position 2, it'll turn on digital output 7. So when we run this, we'll see it reaches position 2, and then right after, that digital output comes on, just 0.5 seconds afterwards. Now, this is a alternate way to do this rather than inserting a line and just turning on, hang on. And just turning on a digital output right after the line instead. The benefit of using the TA and TB is when you are using a CNT value, this digital output 7 will come on a lot sooner. It will come on the second it starts to look ahead in the program. Now, the robot starts to look ahead in the program as it's approaching this point there and considering the CNT value, because it has to look ahead to see if it's going to have to change its path again for another point. So right when it's near that CNT point right there, it'll look ahead in the program and turn that digital output on. If we use the time after, it allows us for a little control in that while we're using the CNT value. The biggest issue with this is you have to use direct representation of these values here when you are using TA or TB. If you instead used a register value for the CNT value or the speed of this motion or some motions around it, it will make the TA and TB unreliable. This was an issue we had at a previous plant and something FANUC did not include in their manual, so I want to make sure this is very clear right here. If you use the CNT as a register or the speed as a register for either this motion or the next motion, the TA will be unreliable. It may turn on, it may not. It may turn on at the same time, it may turn on half a second sooner or later. If you're going to use this, always use direct representation. Mostly TA and TB are used for when you just need to signal that you have entered an area, exited an area, or just to give a notification of something. It's not necessarily the best method to use, but it is an option that you have. Another motion option that you have available is the approach linear distance and the retract linear distance. These are very useful for when you need to guarantee that you're going a certain linear distance either as you're approaching a point or as you're leaving a point. Here's an example of when we use the retract linear distance. Right here we are moving from position 3 to position 2 to position 1. In this case, we want to guarantee that we are moving at least this linear distance before we are moving out. Now, without this linear distance option, you're forced to tinker with the CNT values until you find the value that allows you to start curving here or later. You can't use the CNT 100 because you start curving too soon. CNT 50 means you're a little inefficient right there. When you're using the linear distance option, it forces this distance to be linear as it's going from position 3 to position 2, and then from there it'll use whatever CNT value you give it. So CNT 50 will be the same. That's not being modified at all because it does not interfere with the linear distance. But CNT 100 will start immediately after it's reached that linear distance. This is extremely helpful when you're trying to avoid pins or stacks as you're picking up parts. Overall, this is extremely helpful and an option you should consider using in your program. Be aware though, this is not a very common option that people use, so if you do use this, you should inform the linesman of this option and what it's doing so that they don't delete it or modify it in an incorrect way. Another option is when you're using the approach linear distance. Let's say you needed to make sure that the part you're picking up and dropping is actually dropped on the pins right here. Rather than tinkering with your CNT value, you can find out what that position is directly above there, the linear distance above your actual drop position, and force it to stop curving at that point and then go linearly down. So it works very similar to the retract LD, except this approach linear distance will force it to end its path in a linear distance. So as you can see, a CNT 50 is right there. CNT 100 would curve too long. We need it to finish its curve a lot sooner. So instead we say the approach linear distance is 100 millimeters, forces this ending part to be 100 millimeters, and the robot will calculate to determine the linear distance curve required.